Okay, so we finished the first term of the book. So today the plan was to talk about a bit about lattices. That's what we did, and deterministic lattices, and then we start to discuss random subgroup. As the main motivation at the beginning is to say new stuff about lattices. That's always the case when you give a course for the first time, that you know it's hard to predict exactly. So okay, so that was the first term. So I have only 2 more meetings, and I will discuss invariant on subgroup. The plan was to start with invariant on subgroup, and then to move to non-invariant, more general random subgroup. But we will not do that. We'll just say, give you a bit of taste about the theory of invariant random subgroup. And next year, I'll give a course about random subgroups. So that's a beautiful thing in mathematics that we learned in the last 50 years, that it gives you a lot of advantage to look at things randomly, to add some randomness, and even you can say prove results about deterministic objects by viewing them as probabilistic objects. So that's somehow the philosophy of this. So I want to say new things about lattices, so the family of lattices, and asymptotic invariant of lattices, and so on. So we've seen that lattices are extremely. We already have a taste that it's important objects. It's related to arithmetic and it's related to geometric. And so now we want to view it as a random object. So example of IRS is short for invariant random subgroup. Which I will define what it means soon. But example, if gamma, if G is a locally compact group, and gamma in G is a lattice, so there is a mu probability, the probability measure on G mod gamma. So you can think of it as a probability measure on the conjugacy class of gamma. So there is a map. Consider the map from G mod gamma to the set of discrete subgroup of G, and the map sends the coset G gamma to the conjugate of gamma, G gamma the inverse. So, okay, the image is much smaller than the space of all discrete subgroup, it's just a conjugate class of gamma. But the thing is that when we have a, okay, and you can make it sensible, there is a nice topology here. So this is a continuous map. You can, in particular, measurable, and therefore you can push forward the measure mu to a probability measure here. Push mu to a measure on this space. Let's, for the moment, call this space X. Space of all discrete subgroup of G. We call it X, and we got a measure on X. We get a measure, a probability measure on X, which is invariant. Conjugation is invariant. fact that the measure on G mod gamma was invariant by the G action on this space translate to the fact that the measure we get on X is conjugation invariant. And this is an example of an invariant random subgroup. This is a measure that gives you a random conjugate of gamma. And if you started with a conjugate of gamma, you will get exactly the same measure. So we denote this measure is, let's call it IRS, although I still didn't give the formal definition, by mu gamma. Mu gamma is the IRS corresponding to a lattice gamma, and the conjugate of gamma will give me the same IRS. And you see that in this way, every lattice gives you an IRS. And some measure, probability measure on the space of this discrete group, which is conjugation invariant. And now we want this gives a motivation to study more generally the space of all probability measure on this discrete group, which are conjugation invariant. So the space of all IRSs. So I want to, so because if we can say thing about this space, maybe we can go back and say thing about mu gamma. Mu gamma is a point in some space. If we understand space better, we can say things about a specific point. That's the idea. So the problem is that the space of discrete subgroups is quite complicated. It's not even compact. So I want to consider a larger space, which is the space of all subgroups. So we can forget about discrete for the moment and denote by sub G the space of closed subgroup okay, and we define it for every topological group. I will consider only locally compact group, and in fact, we will very soon consider only Lie groups and only semi-simple Lie groups. So, did we discuss the Chabati topology? No, not in this group. There is a natural topology on this page. I call it the topology of closed subgroup because I never know how to spell the Chabati, but maybe you can help me. U? Yeah. E? No. B? G? Chabati. Why? The Chabati topology.
Hey, that's the question. Does anyone know how to pronounce it?
Chabati.
Chabati? It's fine?
No.
It's not.
No. I heard
I French person pronounce it that way.
I heard Jean-Rambo pronounce it like that. So.
Maybe just because it's French. Like I once, like French.
So when I gave a talk in Lausanne, maybe 2010, when we just had this results about the 7 samurai work, so I gave a talk in Lausanne, and Sarah was in the crowd. So I never been in his talk, but so and then I discussed the space of closed subgroup, and I didn't want to say Chabati. I probably didn't even remember the name. So he told me. So okay. Then you take the natural topology. There is only one. There is the most natural topology, and then no, there are many natural topologies. He didn't like that. But I think that's the natural topology here is can be defined as follows. So usually there are two sets that generate a topology. So one, if U in G open, so you define, let's say, omega U to be the set of all H inside the space of closed subgroup, all the all closed subgroup that intersect U non-trivial. That's one. This I will determine this to be an open set. So and then if K in G is compact, that's another type of open set. Then I can define, let's say, CK to be the set of all H in the space of all closed subgroups such that the intersection of H with K is N. So these are two types of sets, and I determine them to be open, and the Chabati topology is a topology generated by all such sets. This set generates the topology. Okay, first time you see it, it's not so intuitive. So there is an exercise to do. So exercise say that Hn, let Hn be a net of subgroup, or let's say that G is locally compact, sigma compact, and then it's be even metrizable. So the sequence of subgroup converge to a limit if and only if two things. If and only if the following holds. So one is that if Hn size Hn are such and Hn converge to a limit H, then H is in H. Two, for any H, this is the sequence. So for any H in H, let's say this is even a subsequence, you don't even need to take it. For any H in H, there are Hn in Hn such that Hn converge. So that's somehow make it. You see, that's
don't you can really take n into? Don't you need to take like subsequence? Is it possible that for some H you would need like Hn k, which converges to H, not really Hn?
And let's suppose that if G is metrizable, if let's say D is a proper metric in G, so most of these groups are metrizable. So if they're locally compact second countable group, and proper means that balls are closed ball or compact, then you can define then also sub G is metrizable. And here is a metric. You can define the metric, the distance between two groups. To be the integral over R over all positive of the house of distance between the intersection H1 with the ball of radius R. I never know to write the first the point or the radius.
Point.
The point. So the ball of radius R around the identity. The R, and yeah, then you need to make it converge. So let's multiply it by 1 over R square, maybe. So you need it to converge. So you need to guarantee that it converge. So maybe not R square or R cube. Okay, let's do e to the minus R. Hello. So you see basically a sequence, two groups are closed if they're intersected with a large ball around the identity. So we are closed in the house of topology. So most of you know what house of this is, right? So that's it's a metrizable topology. And now sometimes I give it as an exercise. It's not very easy, but it's also not very hard. It's pretty straightforward. That the space is compact. So for us, so let G be LCSC, nobody compact second countable group. Then we have a composition, the space of closed subgroup, which the body topology is compact. So it can be quite complicated, but still compact, always compact. So for instance, it's nice exercise to take a group and to try to understand things about this space. We're not going to it now. For instance, what is the space of closed subgroup of R, the real line? So in the real line, you have the trivial group, and you have the full group R, and you have all the other closed subgroup are just zero or a multiple of zero. So then you can see that it's topologically you get an interval, like a closed interval. It's the space of closed subgroup of R is a homomorphic for closed intervals.
When G is a lead group, is it many?
But for R2, you get it's still a nice space. It will be a two-dimensional, four-dimensional sphere, S4. So the space of closed subgroup of R2 is homomorphic to sphere of dimension 4. It's still a manifold. But if you take more complicated Lie groups, you will get very complicated. So it's compact, but quite compact. And we don't really understand space in general, and it's hard to understand the space in general. So that's not what we do. Instead, we will consider probability measure on the space. So G acts on the space by conjugation. And then the definition of an IRS subgroup is a probability measure, is a G invariant probability measure space. the definition of an IRS, and we saw one example. Let's to say the obvious example, the following one Dirac IRS correspond to normal sum. So if you have a Dirac mass, if you have the probability measure just at a point, you give probability 1 to a point. It means that this point, which is a closed subgroup, is invariant under conjugation, which is a closed normal subgroup, and vice versa. Every closed normal subgroup gives you a Dirac mass. So that's so in a sense, as a mathematician, you see something like that, and then say, oh, okay, we know some theorems about normal subgroups. Let's see if we can generalize them to invariant under subgroups. But it will be even more cool if we can say in some situation new things about normal subgroup by reviewing. So the second example is if gamma in G lattice and mu gamma. And again, so you see that lattices in one hand generalizes normal subgroup, on the other hand generalizes lattices, and okay, and now I'm mostly interested in Lie groups and application to Lie group, but some people study IRSs for other reasons, and in particular, people study IRSs inside discrete groups, which I'm also interested in, because if you start with a lattice, lattice is a discrete group, you study IRSs inside a lattice, and in a sense, it's an IRS in the Lie group because there's a procedure of induction. But maybe, yeah, if okay, today I have some target. I want to show you some theorem. So I'm working on one path in one direction, so I don't tell you everything around, but try to think about all this story in the case of discrete group. You start with a discrete group, try to think what does it mean, the Jaguti topology inside a discrete group, what is the space of every subgroup is closed inside a discrete group, so the space of all subgroup. You consider measures which are invariant under conjugation. In particular, what can you say about the space of all invariant random subgroup in the free group? So that's yeah, and there are many things that can be said, but there are many open problems and some famous problems about invariant random subgroup even in the free group. Yeah, next semester we'll get to that stuff. But here, to get more example, I just want to mention that there is a procedure of induction. Just so if you have a lattice, for instance, in SL2R, the free group is a lattice in SL2R. In the free group, there are plenty of IRSs. Any one of them you can induce to an IRS in SL2R. Or if you have a normal subgroup in a lattice, then you can induce it to an IRS in the, but I will not go into it. I just want to mention that there are some techniques to give more examples. Okay. Results. So we have one result that we didn't prove, but I'm sure many of you know it already, but for those who not, think of it as an exercise. It's doable. It's not hard to find in the literature. And once you have a compact space, and the space of all measure on the space it has a natural topology, which is the weak star topology. You can view every measure as a functional on the space of continuous function. And the space of all probability measure is a closed convex subset of the unit ball of the dual space of the space of continuous function, and therefore by Banach-Halaouglo theorem from functional analysis, theorem implies that the space of IRS G, which is the space of all IRS in G, of all IRS of G, with the natural topology here, which is the weak star topology, this space is it's compact. And this is a good news for us. Because it gives you some compactification. So before we wanted to study lattices, so we want to prove results about lattices. Lattices are discrete objects, and that if you take a group, usually it has only countably many lattices. That's not always true, but for instance, if you take a simple Lie group, which is not SL2R, then it's already true. To have only countably many lattices. Each lattice gives you, so how can you study them as a set? But now you have some compact set which naturally contain this lattice as a point. So you, in a sense, it gives you some compactification for the set of all lattices, and therefore you can take advantage of this compactness and prove results. So, okay. So this space is compact. By the way, a special example of example one, that's a normal subgroup, you can take the Dirac mass on G, which is the probability one, I choose G itself. So this is some special point, and somehow this point, I want to try to ignore it. I want to remove it from the space because I don't know, it's like a boring point. It doesn't give you any information. Also, another one is this one. But this one, this for the moment, for what I want to say now, for my target for today. So today I want to prove some results which I think is very nice about lattices. Using it in invariant shadow. And this point somehow bothers me because, as I told you, IRSs are probability measure on the space of all subgroups. So if you want, we can write it in this way. IRS of G is the space of all probability measure on the Jabuti space of closed subgroup, which are G invariant. So that's some of the G, the exponent here to tell you that I consider only G invariant. But now I want to consider discrete IRS. Let's denote it by IRS B. and I want this to be the set. Okay. So what is that? So definition and IRS mu is discrete if mu of the set of all discrete subgroups with probability 1, when I take a random subgroup, I get a discrete group. So the space of discrete subgroup, it's not always open. It's okay. The space of discrete subgroup is always measurable. So that's meaningful. For Lie group, it's open. So you want an exercise. So yes, okay, this is the definition of discrete IRS. And I want to say something, I want to prove the following proposition. If G, let's say, let G be, let's say, semi-simple Lie group. Probably I want, let's say without compact factor. Actually, let's even focus more. Let's not be most general. So we can just consider simple Lie group, which is not compact. But what I say. So in this generality, also then the space of discrete IRS is compact. So the space of discrete subgroup itself is not compact, but the space of discrete measure, so the measure that gives you probability 1 to choose a discrete group, is compact. So I want to prove this proposition. Because it's valuable, because later we can somehow I want to say something about lattices and more general discrete groups, and I don't want, okay, I want it to be a compact state. I don't want to. So
can all G-invariant measures on discrete subgroups can be extended to a measure, what you call it, pairs of sub-G?
Yeah, it's a measure on sub-G. I consider an IRS mu is a measure on sub-G, but it gives probability 1.
Yeah, that I understand this direction. But if I want to go the other direction, like I have some measure on I had a measure on the discrete subgroups.
Yeah.
Does it come? I mean, maybe I'm losing it. Does it come from some measure?
If you have it
on the whole on sub-G?
Measures push forward.
If you have a set and you have a subset, and you have a measure on the subset, it's also a measure on the bigger set.
Yeah.
There is some notion. Okay.
You just give measure 0 to everything.
Yeah.
But you may ask what is the Borel structure?
Okay.
Does it make sense? But the Borel structure, the topology on the space of discrete subgroup is the topology induced from the space of all groups. So it's a subset of a topological space. The space of all closed subgroup is compact. Sub-G is compact. And the discrete subgroup G is inside is some set. In many cases, it will be open. So I want to give this exercise. Maybe I'll do it after the break, but depending on time. But the exercise. If G is a Lie group, and do you remember what is a Lie group? So let me remind you, a Lie group is a group, is a topological group with no small subgroup.
Locally compact.
NSS, no small subgroup. So a locally compact group is NSS if there is an identity neighborhood which contains no subgroup except the trivial. That's the definition of NSS. And there was a famous problem, Hilbert-Field problem, whether this property is equivalent to Lie groups. And it turned out to be true. But here I need only the easy direction. If you have a Lie group, then it is NSS. There is no small subgroup. There is an identity neighborhood which doesn't contain other groups. And so if G is a Lie group, then the space of discrete subgroup of G is open. It's open and therefore measurable, so that thing makes perfect sense. That's a nice exercise. Yes, it's not closed. You can say things about the closure. For instance, you can prove that if a group is a limit of discrete subgroup, then its connected component of identity is not necessarily trivial, but it's necessarily nilpotent. It may be a larger nilpotent. Like, okay, you can see inside R, you can take inside R, you can take a discrete group, which is a copy of Z. So this would be alpha times Z inside R. And when you take alpha to 0, then this group becomes denser and denser. So in the limit, you will get R. So you see that the limit of this group is not necessarily C, but R is important. So it's not a contradiction to what I say. But you can say things about the closure, but this space is not closed, but it's open. Another result that I want to use is the following. I call it a lemma or fact, I don't know, because I'm not going to prove it. For some of you, I think it's an exercise, but you need some structure theory. So G inside the space of closed subgroup is an isolated form. Yeah, I assume from now on. Let's assume from now on to the rest of the talk today. Let's make this assumption. Let's even do this simple. So let G be a simple non-compact connected that would be a standing assumption until the end of the talk. Okay. Everything I say holds also for semi-simple, maybe automatically, maybe you need to say a few more details, but let me restrict to the case like SL3R, that's enough. So you cannot have a group which is sufficiently close to SLN. If you, maybe we discussed it at some point, but I told you this nice, I think it's nice fact that if you have a Lie group And here actually, you don't even need it to be simple or semi-simple. It could be perfect, like a commutator. So actually, this is actually equivalent to the fact that G has no non-trivial abelianization. So G cannot be mapped onto S1, onto the surface. It's equivalent to it. So inside a Lie group, you have inside a semi-simple Lie group, you have two, you can find two neighborhoods, build identity, such that any choice of a point here and a point here will generate a dense subgroup. Did we discuss this phenomenon at some point? No. So this is actually quite useful result. Maybe at some point I should discuss a bit information about dense subgroups, Lie groups, and maybe in the middle of shot. So you see, if you can recognize this such two neighborhoods, then every group which is close enough to G must intersect this neighborhood and this neighborhood, and therefore it must be dense. But if it's dense and close, then it must be origin. So this is one way to prove this fact. But actually, you can prove it also without this phenomenon. But this phenomenon is useful, so I wanted to mention it. Anyhow, let's take it as a black box. G is isolated. You cannot find something which is sufficiently close to G. You can also think of it in this way. So in G, if you are not discrete, then you are a Lie group of positive dimension. And so the dimension must be strictly smaller, so it cannot be closed. If you go to a vertical, you cannot be closed. If you are discrete, then I already told you that limit of discrete group must be important. So you also cannot be too close, but you have to also to combine these two facts. So if you are not discrete and not connected, then the connected component is normalized by blah blah blah. So it's a normal subgroup. So anyhow, so it's really, this fact is easier than the lemma that was but okay, let's just take it to the black box. G is isolated. I don't want to go into the details. That's here. Next year, everything I promise to do is next course about random groups. So G is isolated. Another fact I want to say is Fürstenberg. Lemma. How should I formulate it? Should I call it G or? Okay, let H inside GLNR say SLNR. B, if you want the minimum assumption, so let's assume that it's non-compact. Only irreducible. Then the projective space has no has no probability measure which are H invariant.
So any action of H?
And
What is strongly irreducible?
there, yeah, I would say, then there is no H invariant probability measure on space, the projective space. So, you know, SLNR acts on Rn, and therefore a line on Rn, which is the projective space. And H is a subgroup, so that's H. I consider different. Later, H will be the image of G under certain representation. Later, I will consider a representation into some linear group.
Given there is no action of H on Pn or for Z action. So, I mean for the natural action.
Yeah.
Okay.
The
So
natural
but it's also that there isn't any action, right? Okay.
Okay.
I wanted to say something.
You can choose different way to formulate the lemma. That's one formulation which is sufficiently good for us. Later we will apply it. When we apply it, we say that situation. What is strongly irreducible? So irreducible means that there is no proper non-trivial subspace which is invariant. Strongly irreducible, so in particular a finite group can act irreducible, right? Like the group of order 4 can act by rotation on R2. And it's actually irreducible, but it's not strongly irreducible because strongly irreducible means that there is no collection, finite collection of proper subspaces which is invariant under that. So if you want the group of order 4 acting by rotation, but preserve this collection of two subspaces. So it's irreducible, but not strongly irreducible. If a group is connected and it's irreducible, then it will automatically be strongly irreducible. So for our case, when we apply later, irreducible and strongly irreducible is the same. But I think if you want to be more general, then you should require that. And what is the proof? So why did I restrict to that situation of subgroup of SLN? Because I don't want to discuss the K decomposition in general, but in SLN you know the K decomposition, right? You know just the polar decomposition, the Gram-Schmidt decomposition. So every metric we can write as upper triangular times so
SON times.
sorry?
SON times diagonal times.
Yeah, excellent. So basically the K decomposition time decomposition sorry?
Is this building safe?
Why?
זה רואה כזה מהסיפור של זה לא יודע.
כן. כן.
גם מולם, גם
סליחה עם הרעשים שלהם.
כן, הרעשים מפריעים יותר מהרעידות. אוקיי, the K decomposition, a clue, so K in our case is SON. But I write KK because you can do it for every semi-circular group. A is the diagonal group. A plus is the diagonal group under the condition with AI reason. And the fact that you know from linear algebra, and if you don't know, then it's an exercise you should do, is that every matrix in SLN can be written in the form G equals K1, A, K2, where Ki are in K, and A in A plus is not a group, it's a semigroup. The reason that you take A plus is because this expression is not unique, but the A part of it is unique. Okay, of course it's not unique because the identity element you can write as K times K inverse for every K. So it's not unique, but it's almost unique in that sense.
You want them to be positive?
Sorry?
You want the AI to be positive?
Yes. How do you prove Kirstenberg lemma? Remember what we just erased? You have H, which is strongly reducible and not compact. So the proof of the lemma, so this I will not prove, that's an exercise. Count me. Basically. And the proof of the Kirstenberg lemma is the following. I want to be sketchy or not, but let mu, suppose mu is a probability measure on the projective space, which is H invariant. Then the irreducibility assumption implies for any finite collection of proper non-trivial I should say I can say with less subspaces. The measure on the projective version of the subspaces is 0. Is right if you have some positive measure. Okay, the measure cannot be supported. The measure is not supported on U is not supported on a finite collection of proper non-trivial subspaces because the support of mu is invariant. Is G invariant and is H invariant. Mu is H invariant, therefore the support is H invariant.
This is not the same statement you wrote. And what you just erased is stronger than what you wrote.
That's what I wrote now is enough. And now consider let Hn in H such that the norm of Hn goes to infinity. By the way, another exercise, what is the norm of G? The operator norm, just A1. So the norm, when I consider operator norm, it's just a norm, like I take a unit vector and I look at its image, the norm of the maximal norm of the image of the unit vector, so then it's exactly A1. Because K acts by isometries, and so you see that Hn goes to infinity. M go to infinity. What it means? It implies that okay, if you write HM, you can write in this decomposition KM AM KM prime. Maybe this is one. Maybe I'll problem with English. Okay. So now, and we know that AM1, this A1 goes to infinity. Up to move it to subsequence, and the product of them is 1. So if AM goes to infinity, then if A1 goes to infinity, then it means that AM n goes to 0 because the product of them is 1. So after moving to subsequence, there is some integer I between n and 1, strictly such that AM I divided by AM I plus 1, there is the jump goes to infinity. Right? It could be that A1 goes to infinity, but A2 goes to infinity on the same speed. And A3, but at some point there is a jump. Okay. And the jump is for single I up to taking subsequence. And I don't know where exactly I want to say it because I want to say it twice. I also want to say that Km converge to a limit and Km prime converge to a limit. Let V be the span of the first unit vector, so E1 up to VI, where EJ is the vector place in Rn. It's a standard basis Rn. Let V be that space and W be the span of EI plus 1 to the n. And so let's actually just V prime and W prime, and let V be K times V prime, where K is this limit, and W be K prime inverse of W. So confusing with all the primes. And then do this exercise to yourself and see that any point which is not in W, or any point P in Pn minus 1, which is not in W, Hm of P converge into V. You see what I have this matrix A1, AI, AI plus 1, AN, 0 elsewhere. If I have a vector which is not in the span of the last coordinates, it's not in W prime, then its image will have something here also. Now you see that the jump from here to here goes to infinity, so you see that the image of such vector will be in the limit inside that space. And now if you play on the right and the left with K and K prime, so you need to change V prime and W prime to that point, but you still get that. So you see that the measure is in the contradiction. Because this implies mu or support of mu is contained in the projectivation of V union projectivation of W, which contradicts the fact that we said in the beginning. So the support of that measure will be inside two spaces, because everything which are outside W is pushed into V. But all these elements that I'm acting preserve the measure. So the measure of everything which is not in V and not in W must be 0. You can't, yeah. Okay, that's a quick proof of the Fürstenberg lemma. This Fürstenberg lemma, so it's not very hard, but it's extremely useful.
Can you explain again the last claim?
This one? So you understood that one?
No, this one.
This one.
Yeah.
Okay, so you understand that if suppose I don't act with K and K prime from the left to right, I just have this diagonal element, and you have a big jump here. So AI divided by AI plus 1, so that is so it's actually AMI and A because you understand, yeah? So you just said that this is the I don't know, my notation are not very good, but I take, but now I think I write it AI, but the elements change because this goes to infinity. Okay, so now you have a vector. So what is a vector? So this, suppose you have a, what is a projective point? I take some representative, which is a vector. I think of vectors up to scalar. I don't care about scaling. So I have A1, AI, AI plus 1, AN.
You just write A1 and 2.
Okay, let's write A1, A2. So, okay, it doesn't matter. This acts on some vector, V1, VI, VI plus 1, and so on. And the result will be A1, V1, AI, VI, AI plus 1, VI plus 1, and VN. And you see,
In the limit it goes to
you see that if the fact that it's not in W means that one of these is not 0. So here I have something, but the ratio between the coefficient here and the coefficient here goes to infinity. All the coefficients here are much bigger than all of the coefficients here. So if here something goes to so the ratio goes to infinity, it means that in the limit I will see a vector which has zeros here and something
not zeros above? Zero
No.
Above big,
Right?
above or big, below the.
Both are big, and you can always normalize because it's up to scale, so you can normalize that the largest one is 1. You can normalize it, and therefore all this must go to 2. Okay? Think of the example if you want. An inverse acting on xy is constant, so you get nx and y, which projectively is the same as 1 and here you take y divided by n squared x, and you see when n goes to infinity, this will go to 0, and the limit you get 1. Okay.
Why does it mean that support is contained in VW?
Sorry?
Why does it mean that the support of mu is contained in?
U is invariant.
Yeah.
And you see that everything which is outside look at the restriction of mu to, look at what happened. Okay, you fill in. So the complement of V, if you want, you can take, okay, I leave it to you. I'm sure you should meditate on this. And so let me just, before the break, I want to write the corollary, which is important for us. And the corollary which is important for us is the following. So X G is simple V group and mu and IRS, then okay, suppose mu has no atom at the group G. So the probability that I choose G, the group G is 0. I told you that G is an isolated point. I want to ignore it. I don't want to choose. I want to look at the interesting part. Then mu is discrete. GB is simple, non-problem. suppose that by way of contradiction, suppose that the probability that the probability of the dimension is equal I is bigger than 0 for some I which is positive. Suppose by way of contradiction, you understand what I wrote here? That's the probability that the random group that I choose is positive dimension. Okay, so okay, we may assume that mu is algorithmic and therefore we can restrict to that invariant subspace of all closed subgroup of dimension I, and suppose we can suppose that this is 1. That the probability that if it's not 0, I can normalize it so it's 1. Okay, let's
invariant.
Do we need ergodicity for that?
No,
Right.
we don't need ergodicity. We may suppose if you want.
It's just invariant sets.
Yeah, it's invariant set. I can restrict. It's an invariant set. If you want, you can assume that mu is not a probability measure, but this is, anyhow, this is the assumption. So, and then for each H closed subgroup, let's consider the Lie algebra of H as a subgroup of the Lie algebra of G. It's a tangent space. The Lie algebra of H. So with probability 1, this Lie algebra of H is I-dimensional. So pushing forward, so you have the map H, you have the map from sub G to the Grassmannian of so that's, if you want, the Grassmannian of all subspaces of all dimension. So you push every H to its Lie algebra. And now push mu, the push forward of mu give you an add G invariant, the push forward of mu gives an add G invariant mobility measure on the wedge product, on, if you want, the ith wedge of the Lie algebra of G. Is it clear what I mean? With probability 1, the subgroup that I take is I-dimensional. I take its Lie algebra, and then in the wedge product, I get a point or a projecting point. So let's take the projectivization of that. And this is the contradiction. So if you want, in the first lemma, you assume that it's not compact, but G is not compact, so the image of G is not compact because it's simple, so don't turn it. Also, you assume strongly reducible, but since G is connected, strongly reducible reduced to irreducible. And the wedge representation may not be irreducible, but G is simple, so it's reductive. So it's so every representation is a direct sum of irreducible ones. So you can project to each irreducible factor. So I just sketch the details, but basically, first angular lemma gives you that. So the Lie algebra of G. By the way, so that's exactly what we want to show. We want to show that it's supported on discrete subgroup. Assuming the contrary, what does it mean that the subgroup is not discrete? It's exactly mean that it has positive dimension. A closed subgroup of a Lie group is always a Lie group by theorem of Kazhdan, and it's discrete if and only if it has its dimension in here. So if the dimension is positive, that's exactly the contradiction. And then we can assume that it's fixed and we get a contradiction to Fürstenberg. So you see, we get Fürstenberg lemma implies corollary that the space of discrete IRS is compact. The space of discrete IRS is compact. So the space of closed subgroup is compact, and therefore by Banach-Uglo theorem, the set of IRSs is compact, the weak are compact. The space of discrete subgroup is not compact, it's an open subset, but the space of measure on that is compact because every measure, since proof, it follows from the previous corollary every IRS is of the form mu is some constant time Dirac mass at G plus 1 minus alpha, something which gives measure 0 to G, mu prime, where mu prime is a discrete IRS. Now, since G is isolated, if I restrict to those mu for which alpha is 0, I get compact. Since G is isolated, for example,
We don't need to be isolated. I mean,
G is isolated in the space of discrete subgroup.
yeah, I mean, the fact we have this decomposition is enough.
Sorry? Yeah, it means that, okay, maybe after I assume that G is, I assume that G is isolated, I said, okay, now look at sub G. Okay, right. A better way to say it is that sub G minus the singleton is compact. And therefore, by Banach-Uglo, the measures on that compact space is compact. But on that compact space, every measure is discrete. Okay, so that's a better way to say that. Now we are in a position that the discrete IRS are compact. And after the break, let's say we come back at 5 to 12, I will try to explain the proof of Kazhdan-Margulis theorem, which is, I think, very nice. In particular, we'll see that a very elementary proof that there is, in any dimension, a hyperbolic manifold of smallest volume. So it's like a, I think, very good fact. You can see easily by considering this notion of IRS. That's one example for the importance of this consideration. So let's meet again at 5. Okay. So I want to prove the following theorem of Kazhdan and Margulis. In half an hour. The theorem says that, okay, let G be a simple limit. Limit. Then there is an identity neighborhood. And such that for every lattice there is a conjugate intersect omega trivial. The theorem is not just for lattices, but I will prove it for lattices. The interesting corollary there is a lower bound on the core volume of lattice. And indeed, proof that V and G be open identity neighborhood symmetric such that V square is inside omega, then the volume of a fundamental domain G mod gamma is at least the volume, the harmonic, and convince itself. So V, such a neighborhood will inject into G mod gamma because if square intersect trivially the fundamental domain, the omega, which okay. So in particular, okay, we had this connection between covolume of lattices and volume of the associated locally symmetric spaces. So in particular, there is a lower bound on the volume of any locally symmetric space corresponding to G. So if you take G to be SL2C, which is the group of isometries of the hyperbolic tree space, then immediately you get that there is a lower bound on the volume of hyperbolic tree manifolds. So that's a fantastic theorem. As we will see, with the terminology of IRS, the proof become, I think this will be enough for the proof. I don't know if I want to be so confident, but it's really completely straightforward. So we need to somehow makes the proper definition. So the proof here is just by making the right definition. The definition. A family of IRSs F, which is a subset of the space of IRS, it's a set of measures called weakly, uniformly discrete if for every epsilon there is U epsilon, ID neighborhood, such that for every U in F, mu of the event gamma intersection with U epsilon non-trivial is less than epsilon. So the probability that you see in a random group an element near the identity, U epsilon near the identity is smaller than epsilon. And it's called weakly uniform. And the theorem, the theorem is that the space of all discrete IRS is weakly uniformly discrete. And this implies, of course, Kazhdan Margulis, so corollary. Taking, let's say, epsilon, any epsilon smaller than 1, let's say 1/2, we see that for every gamma in G lattice, there is a G in G such that G gamma G inverse intersect U 1/2 trivial. So it's implied, so you see it's implied Kazhdan. With probability half, a conjugate will be good with that name. So that's implied Kazhdan Margulis, and it actually gives something stronger, like Kazhdan Margulis, even when you restrict yourself to lattices. And I claim that it's a straightforward consequence of the compactness of the space of discrete IRS. So here is the sketch proof. Let me first give a sketch proof, and then the proof, because the sketch proof is the maybe easier to understand the intuition. The proof itself is hard to sketch. It's only 5 lines, but the sketch proof, okay. So take some epsilon. Suppose by way of contradiction, that for every ID neighborhood, there is UN, same. There is UN IRS. The family, suppose such that the probability that gamma intersect UN non-trivially is bigger than anything. So we imagine, so our group is it's very, of course you can take, so UN, I think of UN identity neighborhood, if you want, I can think of UN to be the ball around the identity of radius 1 over L, or some metric. So it's a simple group. There is even a natural metric there. Coming from some normal Lie algebra. So suppose that for every such UN, I can find mu n. By compactness, of so UN is a descending sequence of identity units. By compactness of the space IRS D of G, UN converge to a limit up to taking substitutes. Now, if you think about it, mu as the property, mu inherit the property that mu of gamma intersection UN non-trivial is positive for every n. But that means that it's not discrete. Contradiction. The contradiction to compactness. So I have a sequence of discrete IRS. I take a limit and I claim that it's not discrete. Why is it not discrete? Because with some positive probability, it intersects every identity neighborhood. Okay, that's
Tsachik.
Ken.
So you pass to the limit mu, and you said it inherits, but like, don't you need to also like say that it's true only for like some kind of the limit of UN? Like, how could you say it's true for each UN exactly?
Because yeah, I didn't write it, but I draw it. The UN are descending. So if you intersect non-trivially U2, you will intersect non-trivially.
Ah, I see. Okay.
So, yeah. But okay. There is some. Okay. When I wrote the proof, I wrote it differently. So let me explain it how it's written in the paper. In the paper, it's also that's the paper, and the proof, I think, start here and it's finished here. So you see, it's like very short. So let me write it as in the paper. But let's now. So that's a sketch proof. One of the. Okay, maybe you can make it complete. It sounds convincing now, but
Explain why it's wrong.
why the proof is wrong?
Mm.
So I want to finish in 19 minutes. So yeah, but we can discuss it later. It's not wrong, but it's not wrong, but things need to be explained a bit more. So let UN be as above. So UN is a descending sequence of compact sets. So let me write. So let UN be a descending sequence of compact. I want them to be close. ID name. And let's now Kn be the set of all gamma inside sub G or sub G, it doesn't matter, such that gamma intersection mu n is 3. Then lemma Kn is open. Proof. I just say follows from no small subgroups, as I said earlier. If you want, should I explain why it's open, or the probability that you intersect?
There's no probability.
What? Not probability, but the event that intersect non-trivially is open because
That's true for me. It's
No.
not hard enough small studies.
it's follow. Yeah, it's linked.
It's not communication.
You can miss compact set or intersect.
Let me just write it.
Oh, right. You can.
Let me write it. Proof. Pick V inside UN. Which contains subgroup, no non-trivial. Which contains no non-trivial subgroup. And V square is also in U. Now I claim that gamma intersect UN non-trivially implies equivalent actually to gamma intersect UN minus V. Okay, because if you had otherwise, the intersection of gamma with UN will be contained inside V. But then it will form a group there, because when you multiply, you're still in UN, so you're still in V. And so.
Wait, why are you still in V?
What?
Why are you still in V?
What? Wait. So let me write it and then ask it. It follows that. Okay, since UN minus V is compact, the level 4. Okay, what's the question?
Can you explain again why did you put that?
If you intersect UN I claim that you must intersect UN minus 1.
Okay.
Because suppose you have a group that intersect UN but miss V.
Okay.
Miss UN minus 1.
Mhm.
It means that its intersection with UN is containing V.
Yeah.
Now, if you multiply 2 points in intersection,
Okay.
they are still in UN because of this property, so they're still in V. So you will see that you will get the intersection in the group. But it's okay. Because, okay. So you have this. So this Kn is open. Okay, now this also solves the exercise that I gave earlier. In the first hour, one of the exercises was clearly Kn are ascending, and the union of Kn equals the set of discrete sums. Every discrete group intersect trivially some UN, some identity name. Therefore, it is in some case. Okay. Okay, now fix epsilon. Let's put it kappa, then I need another name. Some name. Psi n epsilon be the set of all mu in IRS such that mu of Kn is bigger than 1 minus epsilon. Then psi n, this is open. And the union of psi and epsilon over n is the space of all discrete. Right? Because every discrete group, because the union of the Kn is everything, so they, okay. But this is compact. By compactness, there is n0 such that psi n0 epsilon. Why do I carry this epsilon? I fixed epsilon. Psi n0 equals IRS. Okay. If you translate what it means, this implies that U epsilon is U n0 what? If you translate, what does it mean that psi n0 is the full space? It means that every IRS is in psi n0. Means that every IRS gives, for every IRS, the measure of Kn is at least 1 over epsilon, 1 minus epsilon. It means that for every IRS, the probability that you intersect UN trivially is smaller than epsilon, which is exactly. Okay, so that's the. You see, it's really straightforward, and it gives, I think, beautiful results. lower bound on the volume of lattices in particular, but even something stronger. This weak uniform distribution. Yeah, okay, maybe that's enough for today. Some people complain in the break that I'm too slow, so maybe that's why I was too fast after the break. But if I was too fast, then it's still a few minutes for questions. Was it clear? Okay, so next time we'll continue to explain other nice properties of IRSs and how you can apply them to lattices. Yeah, so that's the main motivation to be interested in this whole. Okay, so that's it.
And it's open for scan to be open.